Great. So, right, I'm going to pick up the lecture from yesterday. And yesterday we were talking about topological insulators, and maybe protected by time reversal symmetry. So today we're going to talk about topological crystalline insulators. So this is the last slide that I showed yesterday, which is this table, which is classifying TIs with internal symmetries like time reversal and particle Hall symmetry. And these are the different phases that we discussed yesterday: integer quantum Hall effect, which is topologically the same as a Chern insulator, and 2D and 3D topological insulators with time reversal symmetry. So today I want to discuss the role of crystal symmetries. And the point is that crystal symmetries have two roles in the study of topological phases. They can both protect topological phases and also serve to identify topological phases. And so there's three things that I want to discuss in this lecture. The first is, when we say crystal symmetries, what are we talking about? What are the possible crystal symmetries? Then examples of a few commonly known topological phases with crystal symmetry. And then finally, how do we classify band structures by their symmetry irreps? And so this is basically the theory of topological quantum chemistry and symmetry indicators. So the first question is, what are the crystal symmetries that we're talking about? So there's a few different categories. The first type of crystal symmetry is point group symmetries. And so a point group symmetry leaves at least one point invariant. So this would be like a rotation symmetry, mirror symmetry, inversion, or roto-inversion. And these symmetries together comprise the 32 crystallographic point groups. Then there's translation symmetries. And so once we have these point groups, which kind of define a unit cell, we translate them around to get a crystal. And the translation symmetries can generate the Brillouin lattices in 3D. So these are all the possible Brillouin lattices that you can have. And then finally, there's glide and screw symmetries. These have somehow become into vogue recently because they are elements of non-symmorphic space groups. And so a glide symmetry is a mirror reflection followed by a translation, which is not a full lattice vector. And a screw symmetry is a rotation followed by a partial translation. So I'll show some pictures of those momentarily. But when we're talking about crystal symmetries, these are the only possibilities that we have. And together, combining different point groups and Brillouin lattices, together this gives us the 230 space groups. These are the only possible symmetries that we can have in three-dimensional crystals. So then the next question is, well, how do crystal symmetries act on a Hamiltonian? So we have a Hamiltonian describing a material in some space group. What's the action of symmetry? Well, we're going to talk about this Hamiltonian in momentum space. And so symmetry will act as some matrix operation. So here, let G be some symmetry operator, and delta of G is just a matrix. The Hamiltonian is a matrix. And so the action of this symmetry is that you conjugate the Hamiltonian at some momentum K, and you get back a new Hamiltonian at some rotated or reflected K point. At special points, or rather I should say for each K, we can define what's called the little group. These are the symmetries that leave K invariant. And so you can see that the little group of K plays a special role up here, because when K and GK are the same, then the symmetry will commute with the Hamiltonian. Let me say it differently. The symmetries always commute with the full Hamiltonian, but if G is in the little group of K, then the symmetry will commute with the Hamiltonian at that particular K point. So there's some block, the Hamiltonian is block diagonal in momentum space. And if G is in the little group of K, then that block will remain invariant. And as a consequence, this means that eigenstates labeled by K, so these are the block eigenstates that we talked about yesterday, we can label them by irreps of this little group. And so in practical terms, what this means is we have some band structure. We look at some particular point K, K naught, and all the states will be labeled by some irrep. That's what I'm calling delta 1, delta 2, delta 3 of the group, this little group, which is generated by symmetries that leave this point K naught invariant. There'll be other symmetries that change K naught, say to minus K naught or to rotated K naught, and the wave functions do not transform as irreps of those symmetries. Then we can ask what happens if we move away from K naught And then the points nearby K naught, if K naught has a high symmetry point, its surrounding points will have lower symmetry. And so they will also have a little group, but it will generically be smaller. And so these irreps might split and they'll be labeled by some irreps along this line, which would be irreps of the little group of some neighboring point to K naught. And so we have a set of compatibility relations, which tells us if we know the irreps at any high symmetry K point, we automatically know irreps at the lines away from that K point because of these group theory relations, which tell me if I have an irrep of some group, then I know how it decomposes into irreps of any subgroup. So we can use this to label eigenstates of the wave function. And so this gives us some additional properties for surface states. So I want to compare this to the Chern insulator. So yesterday we were talking about surface states of a Chern insulator, and we talked about we can understand this topological invariant of the Chern number by winding Berry phase. And then, of course, we also talked about the bulk edge correspondence and said how on a single edge, there's a surface state that connects the valence and conduction bands of the Chern insulator. But now, if we have crystal symmetry, we can have additional protection. So generically, if you have two surface states and you don't have any symmetry, these states will gap. And yesterday we talked about an exception to this, which is if you have time reversal symmetry, it can protect it can protect a crossing like this, two surface states crossing each other, and prevent it from gapping. But the crystal symmetries can do the same thing as long as they're preserved on the surface. And so I'll show some examples of this. And so I think that the first most straightforward example is a mirror Chern insulator. And so, so what's the action of mirror symmetry? Mirror symmetry is a reflection of one coordinate. So it takes x, y, z to minus x, y, z. So it's reflection across this plane, say. And in momentum space, it does the same thing. It takes kx to minus kx. And so that means that for this plane where kx equals 0 in the Brillouin zone, this plane is invariant under mirror symmetry. And so that means we can simultaneously diagonalize the Hamiltonian with the mirror operator. And we'll see that the eigenstates will split into two sectors. They either have a plus mirror eigenvalue or a minus mirror eigenvalue. And so then within each one of these sectors, we can compute the Chern number of a single sector. And that gives us two Chern numbers, a Chern number of all the bands with plus mirror eigenvalue and Chern number of all the bands with minus mirror eigenvalue. Note, this is in particular something, it's a 3D property because this mirror plane, we need to be 2D because we want to compute the Chern number of some 2D plane. If we only had a 2D system, then instead of a mirror plane, we'd have a mirror line and it wouldn't have a Chern number. So we can compute the Chern number for each one of these mirror sectors, and this gives us a refined topological invariant, which is different than the total Chern number. So the total Chern number would be C plus C minus, and the mirror Chern number will be the difference between them. And so for surface states, this gives us a new possibility. If we have a mirror Chern number of 1, that means that on each edge we have one band with Chern number +1, say in the plus I mirror sector, and another band with Chern number -I in the minus mirror sector. And in addition, there's other, so this would also be a TI, because you can see that there's this Dirac cone on the surface. But there's other possibilities which we didn't see yesterday, which is that mirror symmetry could also protect 2 Dirac cones or more Dirac cones on the surface. And so the point here is that with extra symmetry, we can get different types of surface state configurations that we couldn't get before with just time reversal symmetry.
Hey, Jennifer, there is a question actually which might be relevant for the. So can you comment for chiral symmetry?
Can I comment for chiral symmetry? Is that the end of the question?
Yeah, it says anonymous attendee asks, can you comment for chiral symmetry?
Yeah, so usually chiral symmetry gives a type of so a chiral symmetry is usually also considered an on-site symmetry. So that would be along the lines of time reversal, and it leaves each point invariant. And a chiral symmetry will be like a particle hole symmetry. So a chiral symmetry will give us an extra constraint, which is like this top picture, for example, would be able to be to satisfy chiral symmetry because it's particle hole symmetric. This lower picture wouldn't. But importantly, chiral, so I wasn't going to say anything about this, but the chiral symmetries are what protect superconductors. And so usually when we have mid-gap states, so say you have a state at zero energy in some electronic system, there's nothing to pin that state at zero energy. It could move up or down. And the thing that makes a topological band is that you have surface states that span all the way across from valence to conduction band. So even if you move them up and down, you still have gapless surface states. Chiral symmetry, which is like a particle hole symmetry, does something different. It takes E to minus E, and that results from a Bogleibov-Degenn equations for superconductors. And so with chiral symmetry, if you have one state at zero energy, there's nothing that can move it. And so even if you don't have bands that connect conduction and valence bands, having a state at zero energy is quite special, and it would actually be topologically protected by a chiral symmetry. So chiral symmetries describe the surface states of topological superconductors, and they can protect states at zero energy in a way that wouldn't happen for a regular electronic system.
Let me just comment. I'll actually discuss this in my lecture, so if you stay tuned, then so you don't need to worry more.
Great. So that's everyone's motivation to keep listening till the end of the week. Thanks, Vitas.
Okay. Thank you.
Okay. Great. That's great. Okay, good. So good. So back to the crystal symmetries. The point is crystal symmetries allow for more types of surface states than otherwise. And I want to point out, which will kind of be a theme, that this mirror Chern insulator, which was predicted, I think, in 2011, as a phase of matter, was actually observed in the following year. And so these are this is the prediction of this ab initio calculation. This is one of the mirror Chern surface states. This is only half the Brillouin zone. So there's a second mirror Chern surface state, which I didn't show here. So this has mirror Chern of 2. And this is the experimental observation, which is ARPA's data, which is showing the part of the Dirac cone, which is below the Fermi level. One of the things that makes this field of topological crystalline insulators so exciting is that there's been this rapid back and forth between theoretical predictions and experimental observations. I'll show a little bit more of that as we go on. Okay, so next I wanted to bring up as a second example, topological insulators with inversion symmetry. So inversion symmetry it inverts all points. X, Y, Z goes to minus X, minus Y, minus Z, and same in momentum space. And so we can only assign inversion eigenvalues to wave functions at k points that are inversion invariant. So kx, ky, kz needs to either be 0 or pi. These are the same as the trim points. So inversion invariant means the same thing as time reversal invariant, because time reversal also takes k to minus k. And so just to point out something kind of, maybe it's obvious, in 2D, there's always 4 trim points, and in 3D, there's always 8 trim points, and this doesn't depend on the type of lattice that you have. So yesterday I showed this formula for the Z2 topological invariant, and what Fu and Kane later showed was that you can compute this invariant in a more simple way from the inversion eigenvalues. So if you take the inversion eigenvalues of all the occupied bands, take one from each Kramer's pair, multiply those together, you'll get a plus or a minus 1, and that gives you the Z2 invariant. So this is an instance where inversion symmetry can identify the topological phase, even though it's not protecting the Z2 phase. If you broke inversion, you would still have a topological insulator. The role of the inversion eigenvalues here is just to diagnose it. This is different than the mirror Chern insulator, where the mirror symmetry is actually protecting the topological surface states. And if you broke the mirror symmetry, you would gap out those surface states. So this is what I mean by how symmetries can both protect and identify topological phases. So just to show in practice how this invariant works, this is a schematic picture. Actually, it's from this website that I'll discuss later, of the band structure of bismuth selenide. So bismuth selenide is a well-known 3D topological insulator. And so its trim points, because of the lattice, it has these kind of weird labeled trim points. but they're all, so it's called gamma, L, F, and T. And for each one of these trim points, I drew a minus sign if it has negative inversion eigenvalue, and if there's no sign, it means positive. And so for each one of these trim points, we can compute the product of inversion eigenvalues. And what we see is that there's only one point, which is gamma, which has a -1. So if we multiply these together, we get -1, and that tells us that business selenide is a 3D TI. Okay, and then the last example that I want to show, coming back to these non-symmorphic space groups, is an example of surface states protected by glide symmetry. So this is the crystal structure, one of the examples of the crystal structure of a glide non-symmorphic topological insulator. So just to show how these glide and screw symmetries work, a glide symmetry is a reflection through this plane followed by a translation of half a lattice vector. So the full lattice vector is going from blue to blue. So this crystal does not have a mirror reflection as a symmetry, because it would exchange these two atoms, which are different. But what it does have is mirror reflection followed by a translation of half a lattice vector. And that's what the glide is. And similarly, it also has a screw symmetry. So if you try to do a 6-fold or 2 pi over 6 rotation, this crystal doesn't have that symmetry, because that rotation would exchange these two atoms. But if you do that half rotation, 2 pi over 6 rotation, and then half a lattice vector translation, then you'll get back to your same starting point. So this is an example of a crystal in a non-symmorphic space group, which has glide and screw symmetries. Now, so the glide symmetry in real space, it takes x to minus x and then translates by a half in the z direction. If we square this symmetry, then, so if we perform this operation twice, x and y will be invariant, but z will go to z plus 1. So this glide symmetry squared gives us a full lattice translation. So that's what I'm trying to say down here. If we square this symmetry, we'll get a translation in the z direction, and we also get a minus sign, which comes from doing the mirror reflection twice. And so since we know that a translation in the z direction is implemented by a phase e to the I kz, then the eigenvalues of this operator must have a phase e to the I kz over 2. Sorry, there's a minus sign, I didn't say, e to the minus I kz over 2, and then this factor of plus or minus I out front. So the weird feature of eigenvalues of glide symmetries is that they depend on k. They're not just fixed numbers. So what's the impact of this on surface states? In combination with time reversal, we can get what's called hourglass surface states. So I'll try to draw a schematic of how this works. We have our conduction and valence bands here. Suppose we have one surface state. Suppose its glide eigenvalue is plus I at the origin. Then we can see by looking at this formula, a band that has eigenvalue plus I at the origin moves to have a phase of 1 at the other side of the Brillouin zone. But from time reversal, we know that at both trim points, this band needs to have a Kramer's partner. So plus I will have a minus I time reverse partner. That will be the start of another band. And a band which has minus I eigenvalue will go to -1 at the other side of the Brillouin zone. But now we have two states here which are not Kramer's partners, because time reversal symmetry would relate states whose eigenvalues are complex conjugates of each other, and these are real, so they're not complex conjugates of each other. So there must be more surface states, and so they get filled in some configuration like this. So the surface states always need to come in groups of 4, and this is called an hourglass because it kind of resembles the crisscross shape of an hourglass. And there's another possibility consistent with this, which is called glide spin Hall. You can see that if there's the other possibility is if the surface states go from conduction to valence band and keep going in this way and don't cross each other, this is also consistent with the glide symmetry.
Jennifer, there is another question. Is it possible to open a boundary that protects these glide symmetries?
Yeah, so right, so there's something important here, which is that actually maybe it's good to go back to this picture. The glide symmetry, any type of crystal symmetry might be preserved on only some surfaces. And so a glide symmetry, the one that we've been talking about, which has a translation in this direction, it's only going to be preserved on a surface which is, let's see, it has to, this translation vector must be one of the surface vectors. And then the other one must preserve this mirror. So it must be going out of, I guess, out of the page so that we can preserve this mirror symmetry. So there's only one particular surface which will preserve glide symmetry. And if you look on other surfaces, there's no reason that you would have these special surface states. So yes, you can look on the surfaces that break glide symmetry, but you won't then have surface states that are constrained. And same with the mirror Chern insulator. You need to, if the mirror Chern insulator is there's some mirror plane and it is reflecting this way, then you need to look at the surface, which is kind of perpendicular to the mirror plane, so that points on that surface reflect to each other. So this is the difference between on-site symmetries and crystal symmetries. You can only expect to see surface states on surfaces that are preserved by that symmetry. If you have a Z2TI protected by time reversal leaves every site invariant. So no matter how you truncate the system, you'll always see surface states. So that's an important difference. Okay, so right, so glide symmetry can protect these kind of special looking surface states. And in particular, there's actually two lines in the surface Brillouin zone that will have this property, and so then you can connect them in different ways. And so there's different possible ways to connect these surface states, some of which have what's called spectral flow. That is, there's always some band at any given energy, there's always bands crossing the Fermi level, and some of them don't have this kind of flow, and that just depends on the bulk invariant. And so there's a Z4 invariant, which is corresponding to all these different possibilities, which was classified in this work. And we also commented on it in this second paper. And following on this theme of topological crystalline insulators predicted and observed. So this, the prediction in potassium mercury antimony was predicted in 2016. And then there's this observation from 2017. The data, you need to fit the data to see this hourglass because it turns out to be very squished at one end. But from the data they have, it seems consistent with this ab initio prediction. Okay, so now what I've shown so far is a classification of topological crystalline insulators with different types of symmetry, mirror symmetry, glide symmetry, and then also the role of inversion symmetry. And so you can see that if we proceed in this way, it seems a little bit ad hoc, like we're picking different symmetries and classifying them, but there's 230 space groups. Most of those space groups have multiple symmetries. So what's the full classification? And so that's the question that we set out to answer a couple of years ago. This has kind of two parts. The first part is, if we have some particular space group, what are the possible topological indices? And in particular, if you have multiple different symmetries, how do these indices interplay with each other? And then the second part is topological indices are formulated in momentum space, but crystals are classified in real space. So is there an efficient way to find topological materials? And so I'll spend the rest of the talk kind of trying to answer this question. This picture is meant to show, suppose you have some band structure, you have some group of valence bands. What's the topological index of these bands in any space group? That's what we want to know. And so these are the kind of key references, our paper and also a parallel paper which are trying to answer these questions that I just posed. And these papers are similar in the main idea. What I think is the main idea is that topological bands are those which we can't deform to atomic limit bands. And so yesterday we talked about this. There's insulators and there's different types of insulators. And if we start with an atomic limit, which is all the atoms spread far apart, no hopping at all, then you'll get completely flat bands. And once you start introducing hopping terms, as long as you don't close the bulk gap, then those band structures will be topologically equivalent to an atomic limit. A topological band structure, which is not equivalent, would require a gap closing and reopening. And so a topological band should be one which is not deformable to any of these atomic limits, because all of these atomic limits are going to be our definition of a band insulator. So that's what the key idea is. Topological bands are those which cannot be deformed to an atomic limit. And using that as our starting point, then what we want to do is identify all atomic limits. And so I'll describe a scheme by which we can enumerate all of these. And then we can look at their symmetry eigenvalues. And so we're going to build up a list, which is a list of all of these atomic limit phases. And for each atomic limit, all the symmetry eigenvalues at different high symmetry points. Then we'll be able to answer the question that I just posed, which is, now you give me some band structure, you have some valence bands. Are these topological bands? What we can do is look at the symmetry eigenvalues of those bands and compare it to our list of trivial bands. And if those eigenvalues aren't consistent with any trivial band or any sum of any trivial bands, then we know that those bands cannot be deformable to an atomic limit. Because if they could be deformed, then they would have the same eigenvalues as an atomic limit. And so in this way, we kind of have a key by which we can identify topological phases by their symmetry eigenvalues. So the majority of what I'm going to say for the remainder of this talk is this point one. How do we identify atomic limits? How do we compute their symmetry eigenvalues? And once we do that, then point two is straightforward, because we identify the topological phases as those which don't match any of these trivial eigenvalues. Okay, so to this point, how can we identify all of the atomic limits? First off, we need to treat each space group separately. So fix one space group and just talk about that space group. Once you fix the space group, that doesn't fix the ways that atoms can be arranged. And so, for example, I'm showing a 2D example here. We can consider the group which is generated by C6 rotation and mirror symmetries. So if we consider a group with those operations, then we can have a triangular lattice. But we could also have a honeycomb lattice and a Kalgame lattice. And all of these possibilities have a 6-fold rotation, and they also have a kind of up-down and also left-right mirror symmetry. So within one space group, there's many ways to arrange atoms, and we can classify them by what's called the Wyckoff positions. So what this means, the difference between different Wyckoff positions is what is the symmetry that leaves one atom invariant. So if we look at the triangular lattice, for example, this atom is invariant under a 6-fold rotation symmetry. If we look at the honeycomb lattice, each atom itself is not invariant under a 6-fold rotation, but the 6-fold rotations move the A and B sublattices into each other. That's why on triangular lattice, there's one site in the unit cell, but honeycomb has to have 2 sites because the 6-fold rotation does not leave one site invariant, but maps it to a partner. And then if we look at the Kalgame lattice, also each individual site is not invariant under 6-fold rotation. They also map to each other under 6 folds, but each individual site is now invariant only under a 2-fold rotation. And so then there has to be 3 sites in the unit cell. So these different, within each space group, the different ways you can arrange atoms are classified by what is the group that leaves each atom invariant. The second aspect of this is so now suppose we pick our space group and we pick our Wyckoff position. So we could look at the honeycomb lattice. Then there's still another question, which is each atomic limit should be classified by a choice of orbital. So you can think of this as making a tight binding model. If you make a tight binding model, you need to choose which orbitals are going to enter the model. And for each different choice of orbital, you will get a different atomic limit, which has different symmetry properties. So I just drew some examples here, but the point is that space group, Wyckoff position, and orbital, these things together define the atomic limit. And any subset of those does not uniquely define an atomic limit.
Jennifer, there is another question in the Q&A box. Does the closing of the band gap when deforming from the atomic limit have to be at the high symmetry K point? What happens if the bands touch midway between 2 trim points? Yeah,
so right, the band crossing does not always have to be at a high symmetry point. That depends on Right, that depends on which space group you are in. So let's see. So for example, you could have, there's many ways in which this could occur somewhat trivially. You could have some valence band, you have a bunch of valence bands, and maybe in one place, a valence band is kind of sticking up a bit higher and the conduction band sticks up lower. These things can gap each other along some, some low symmetry point. That will not change the topological invariant. Yeah, so that will just, right, that will not change the topological invariant, but it can certainly happen.
Okay.
And sometimes that can also create Weil points in the band structure. So it may be that such a crossing cannot gap, it'll remain gapless. And so that will change the properties of material. But if there's some crossing and then it becomes avoided and a gap opens away from a high symmetry point, then usually that does not change the topological invariant. Okay, great, good question. So, right, so now we've defined what we want to call the atomic limit, and we can enumerate these things by all the space groups, all the Wyckoff positions in each space group, which are listed, and all possible orbitals. I want to try to give some insight now. Once we have that information, why is the symmetry of the lattice completely determined? What does that mean? So suppose we start with this honeycomb lattice and consider just one point on the honeycomb lattice. I call this point Q. There's some symmetries that leave this site invariant. Like I said, that's what classifies the Wyckoff position. And so whatever orbital is on this site has to be a representation of this site symmetry group. So in this case, it could be s orbitals, pz orbitals, but px and py orbitals would transform together as a single irrep because they get mixed under these symmetries. So once we pick our Wyckoff position and we pick our orbital, we know something about symmetry, but it's just the symmetry of one single site because it will be an irrep of the site symmetry group. But now there's the other symmetry operations that take your site Q to some partner site. And so if we know which orbital we have on Q, then we can act with the rotation and get the orbital on this other site Q2. And we can continue in this way. We can act by translation and get the orbital on some other site. And so if we know the symmetry of just the one orbital or orbital set, which is some irrep of the site symmetry group on one site, then we can use the other symmetries that don't leave that site invariant to tile the entire lattice. And every single other atom is going to be, or every single other orbital is going to be connected to our original orbitals by symmetry. So once we specify this data, we've determined the symmetry of every single other site on the lattice. And we can think of this as basically a big matrix. That's how you think of representations of a group, or at least that's how I think of representations of a group. We could think of a big matrix where the rows and columns are labeled by these atoms. So these are all the different blue dots. Each one is some position. And there's going to be some, for each symmetry operation, there's going to be some diagonal elements for the symmetries that leave Q invariant. So if G is some symmetry that leaves Q invariant, then in this matrix, it'll be a diagonal block. And if it mixes two different sites, say if it mixed Q and Q3, then there'd be these off diagonal blocks. And so this is some infinite matrix, and we could fill in all the elements by saying, how does the symmetry act on this site Q? And how does it take us to some other site by this set of symmetry operations? And the point is that for each symmetry operation in the space group, we can build up such a matrix in this way. Just to say it for people who have some experience with group theory, formally, there's a formal way of doing this besides this kind of hand-waving idea of moving atoms around on the lattice, which is if you take your representation of the site symmetry group and call it rho, that's a representation of the site symmetry group, which is a subgroup of the full space group, so it can induce a representation of the full space group. And this induction procedure is unique. So what that means is once you know the orbitals on that particular site, you can get a representation of the full space group, and there's no ambiguity in getting it. And that's exactly what this big matrix that I'm drawing schematically represents. if we Fourier transform this thing, then we can get an equally big matrix, which is now labeled by K points. And the diagonal blocks here are going to be elements in the little group of that K point. And so whatever block is here will correspond to these labels at that K point that we were talking about at the beginning of this lecture. So now we've shown that if you pick your space group, Wyckoff position, and orbital in real space, make this matrix, which is uniquely determined, Fourier transform it, you will uniquely get out, or I should say deterministically get out irreps at all the different high symmetry K points. And then we can determine the irreps at the low symmetry K points by these compatibility relations. And so this is all completely determined. So just to give a quick example of how this works, these matrices that I'm talking about, suppose we consider a 1D lattice of S orbitals with inversion symmetry, then our group has identity, inversion, and translation as the symmetry generators. Identity matrix, obvious. So what would be the inversion matrix? It would mix the site X and minus X. And so it would be kind of completely off diagonal in real space, some infinite matrix. And then similarly, we could translate by 1. So that would take the site at -2 to -1, -1 to 0, etc. So that would be kind of the lower block below the main diagonal. These are the matrices that I'm talking about. And then we can Fourier transform them to get the irreps in momentum space. We can do the same thing for p orbitals. The difference is that the inversion matrix has minus signs now. And so if we repeat this, what we see for these two examples we just discussed, the S and p orbitals, once we Fourier transform, we get inversion eigenvalues at k equals 0 and k equals pi. And for s orbitals, they're both plus, and for p orbitals, they're both minus. We can consider a different 1D lattice where the inversion center is here and the atoms don't sit on the inversion center. And this changes the inversion eigenvalue at pi. And you can think of this because what is the eigenstate at pi? Well, it's a wave function in the basis of atoms, which has plus minus phases on all of the sites. And so previously, when the inversion operator, like if we look up here, the inversion operator would map this site to itself. It would map these sites, which at k equals pi would have the same phase to each other. So you get an inversion eigenvalue of +1. But in this case, if we have at k equals pi, these alternating plus minus phases, the inversion operator will map states into each other which have opposite phase. And so you get an inversion eigenvalue of -1. And similarly for p orbitals, when you had minus minus, you now have minus plus. The important point here in 1D is that we now have these 4 different atomic limits, and we have these possible eigenvalues and inversion eigenvalues in momentum space, which are plus plus, minus minus, plus minus, minus plus. Those are all 4 possibilities. And so this means that in 1D, any combination of inversion eigenvalues can be understood as an atomic limit, as one of these atomic limits, because there's only 4 possibilities. Question?
Yeah, actually there is one from Mikel Iraola. Following the idea of the previous question, how can we make sure that there are not crossings in generic points like value points if we calculate the band structure only in lines connecting high symmetry points, not in all K points? Yeah,
so there's a couple answers to this. One answer is that if you have a vial point at some low symmetry point, and you only look at your bands at high symmetry points, vial points separate planes with different Chern numbers. So I'll talk more about that on Friday. But so if one of your planes has Chern numbers, can also be identified by crystal symmetry, but only mod the index of crystal symmetry. So if you have a 2-fold rotation, they can be only identified mod 2. In other words, a Chern number of 1 can be identified by C2 rotation eigenvalues, but a Chern number of 2 could not be. So to some extent then, if you had a vial point and you looked at different planes, high symmetry planes on either side of the vial points, you could identify the fact that you had a vial point in between by seeing that one of those planes has a Chern number and the other plane does not. But that's of limited extent. So that's basically the extent to which you can identify vial points by crystal symmetries. you can look at the gapped planes and pick them up. But there's going to be cases where you look at there's going to be cases where just by looking at high symmetry points, you couldn't tell that you had a gapless band structure. Not all gapless band structures can be identified in that way. And so the symmetry indicators are of great utility, but not unlimited utility.
Thank you.
Great. So, so the thing that I want to say here is that in 1D, every combination of inversion eigenvalues can be understood as an atomic limit, but in 2D, this is not the case. And so that's one reason why in 1D, you can't have topological phases that don't have atomic limits. Because we just showed there's only 4 possible inversion eigenvalues and they each correspond to an atomic limit. So in 2D, this is not the case. So, so these are all the possible inversion eigenvalues that you can have. And what you can see is that in each one of these lines, these are all the trim points, there's either 0, 2, or 4 minus signs. You never get an odd number of minus signs. And so this is the justification, a backwards justification for the inversion eigenvalue formula proposed by Fu and Kane. You can see that if you only have 1 minus sign, then it's inconsistent with any of these atomic limit phases. And so you must be some kind of topological phase. And you can do a similar calculation for 3D and get the same result. So, okay, so that's how this would kind of work for inversion eigenvalues. And so what we now want to do is extend this to every single space group, every Wyckoff position, every orbital. We want to compute all the symmetry eigenvalues. But the problem is that although there's only 230 space groups, there's only a finite number of Wyckoff positions, but there's infinitely many choices of orbitals. And some of these Wyckoff positions are movable, so they have variable coordinates. So in that sense, there's infinitely many Wyckoff positions. And the necessary leap that we need to make is that actually we don't need to compute all atomic limits. We just need to compute a finite subset of them, which are called elementary. We call them elementary band representations. And from this finite subset, every other atomic limit is can be thought of as a linear combination of this. So that's the key step. These elementary band representations, which you might have heard of in the literature, gives us a basis set of atomic limits from which every other atomic limit can be built from. So for example, say I have d orbitals. D orbitals may not be an irrep of some site symmetry group, but they will decompose, say, as a sum of 2 irreps, and each one of those sums will be the elementary band representations, and the d orbitals would be obtained as a combination of those. And there's just some rules to show how we can find the elementary band representations. So there's only finitely many of these, we call them EBRs, and this is our basis set for atomic limit phases. Just to say, that finite number is quite large. So you can understand how large it is by a rough estimate. 230 space groups. Usually there's a few, say 3 Wyckoff positions in each space group. And then there's a few, say 3 irreps of each Wyckoff position. That already gives us the number 2000, which turns out to be a good rough estimate. We can split up these EBRs into whether or not they have time reversal and whether or not they have spin orbit coupling. And there's, you can see the numbers here, more or less 2000 for each category for a total of 10,000 total EBRs. So there's a lot of these atomic limits, but the number is still finite, and that's what makes the problem tractable. And so this is kind of the main punchline of this theory of topological quantum chemistry. We have this algorithm by which for every atomic limit phase, we can compute the irreps in momentum space. And furthermore, for every single space group and every Wyckoff position and every orbital, all of these phases are uploaded or programmed into the Bilbao Crystallographic Server website. And so this was a great collaboration that I was part of with, including, of course, one of the key organizers of our workshop, Maya, as well as some of the other speakers in the workshop, and hosted by this Bilbao group at the DIPC and the University of Bilbao. So I just want to show how this website works so that you have some flavor of it. You can go to the website you can enter a space group number, and then you can click on one of these tabs to get the band representations with or without time reversal. And then when you click on it, you get a table like this. And how do I read this table? The first row is a Wyckoff position. So that's like what this 1A is meaning. And then there's 2B and the table keeps going. And then the second row is telling me about orbital content. And so for each one of these 1As, I can consider all these different orbital types. And like we said, each one of those is a different atomic limit phase. And for each one of these phases, the symmetries in momentum space at the high symmetry points are completely determined, like we discussed, by making these matrices and Fourier transforming them. So you can get these labels. And so now we can do, I should say, each one of these labels kind of acts as a symmetry indicator for this phase. Now we can carry out the program that that I discussed. If we now have some mystery band structure with some valence bands, and we want to know if those valence bands are topological, we can look up their irreps. We can compare them to the server, and we can see if they do not appear on the server, then they're definitely not an atomic limit phase, which makes them topological bands. Question?
Yeah, there is another question from Mikel Garcia. Are EBRs overcomplete? Can a set of bands be consistent with more than one decomposition involving,
yes,
in each case, different Wyckoff positions?
Mm-hmm. Yeah, this is actually a very cool question. So there's two, I guess, a couple of ways to answer this. Yeah, the EBRs are they form an overcomplete basis set. So there's cases where if you have multiple orbitals on some Wyckoff position, you could deform them while preserving symmetry to some other Wyckoff position. So there's kind of a multi-correspondence, and those things are identical to each other. If you can ever, it's actually easiest to understand pictorially. If you can ever take your orbitals on one site and while preserving symmetry, move them to some other site, then that will produce seemingly two EBRs, but actually they'll be equivalent. Now, there's another interesting thing, which is that there can also, this is subtle, there can also be distinct EBRs which have the same symmetry labels in momentum space, but are not the same as each other. And so we actually recently, just this year, posted a paper. You can find it, I didn't reference it anywhere in these slides, but you can find it, one of my more recent papers on the archive. It's called Topology Invisible to Eigenvalues. There's different atomic limits which have the same eigenvalues, but they can be distinguished by different types of Berry phases or Wilson loops. And we've listed all of these and given some examples of how you can classify them.
Okay, thank you.
Okay, great. So, right, good. This is I think this is the end of my talk. So now we can carry out this scheme to, so the first question I asked was, if we have a band structure and we have some bands and we want to know whether they're topological, how can we accomplish that? Okay, we accomplish it by comparing their eigenvalues to all these atomic limit eigenvalues on the server. We can now answer the second question, which is, how can we find topological materials? And so this is a calls for a high throughput calculation, which is, you can take every known reported chemical compound, these are accumulated in various databases, compute the band structure, compute the symmetry irreps, and actually you really only need the irreps at high symmetry points, and then compare to irreps on the server and automate this process. And so this is a massive project which was led by Maya and also Andre, completing this task. And so this is what the content of this website, topologicalquantumchemistry.com. And there's also a parallel website called Materia, which is led by Chen Fang's group, which does the same thing. And so if you're interested in this, you can check out these websites. You can click on different elements, search for materials, and it will tell you the irreps at high symmetry points and tell you also whether it's in a topological phase or not. And so I guess, earlier I showed this reference by Poe et al., where they coined the phrase symmetry indicators. The idea here is that by looking at all these, I'll say it in the language that I've been using, by looking at all these combinations of EBRs, you can identify rigorously using group theory, you can identify which possible combinations of irreps are not EBRs and not sums of EBRs. And you can get a group structure out of that identification. And so for each space group, you can make an invariant, which would be like Z2 or Z4. And that's the content of these symmetry indicators. And so if you look at this website, it will tell you for any particular material what that invariant is. And it will also tell you the irreps at all the high symmetry points. Okay, so in summary, these are the main points that I would like people to take away. Crystal symmetry can both protect and identify topological phases. We discussed a few interesting canonical and also more recent examples. And then finally, this concept of elementary band representations gives us a way to enumerate atomic limit phases and therefore identify topological phases. And I will advertise some recent review articles that I've been a part of. So the first one by myself and Barry Bradlin is a review article in Annual Reviews of Condensed Matter Physics. It's also posted on the archive, where I think we've given a pedagogical summary of how you can actually compute these band representations and how the group theory works in kind of layman's terms. So that's some place where I would point you if you want to understand this theory better. And then recently we have another review article here, which is also on the archive, which is more about the material side, how to identify topological materials and the kind of chronological story of different types of TIs and TCIs. So I will stop here, and I think that leaves a few minutes if there's any final questions.
Yeah, thank you, Jennifer. There is actually one question in the Q&A box. Is using EBRs, can you define fragile phases?
Yes, great. It's almost like I could have planted that question. That's a great question. So the fragile phases can be thought of as a difference rather than a sum of two EBRs. So I've kind of mentioned how we can add EBRs together, and that's very intuitive. Say I have some atomic limit of s orbitals and then p orbitals. Any crystal will actually, the band structure will actually consist of many different types of orbitals, and so adding them is very intuitive. What does it mean to subtract them? It turns out that there's certain phases which don't have an atomic limit, but their eigenstates or irreps at high symmetry points are consistent with subtracting two EBRs. And so that's what fragile topology is. It's fragile because if you added in the missing EBR, so say you have two EBRs, 1 and 2, and that maybe I should call them A and B. If you then considered a different band structure where you added in additional B bands, if your EBR was like A minus B, you would get a trivial band structure consistent just with A. That's considered fragile because what we would want for a strong or stable topological phase is that no matter what trivial bands I added, if I had, you want topological plus trivial equals topological. That's what stable means. No matter what trivial bands I add to my topological phase, I'll always get back something topological. Fragile phases don't have that property. You can have fragile plus trivial equals trivial. And you can see these from the EBRs by subtracting those symmetry labels. The fragile phases, the symmetry indicators, the Z2 or Z4 or Zn index that I was mentioning, that doesn't actually detect the fragile phases. That's only detecting stable phases. And so the symmetry indicators by Poe et al. And our work on topological quantum chemistry using EBRs are complementary in that way. They kind of have a different definition of topological.
Okay, thank you. There are no more questions. So on behalf of everyone, I thank the speaker again and hope to see you tomorrow at the same time. So yeah, let's have a break, like 20 minutes. We will reconvene at 5 p.m. here in Europe. I don't know what time is there in US or in Asia, but let's have a coffee and we will start again with the last talk by Andrei Barnavik. So hope to see you. Thank you, Jennifer.